Okay, hello and welcome. And so, what we are going to be doing is we are going to be looking at this a little. So we are going to. This is going to be a very short lecture. But before we go on to what we want to do for the day, let me just remind you that we looked at trying to understand, general discussions about Lie groups and Lie algebras earlier. We said that when we have these when we have some group elements G, which depend smoothly on a parameter alpha, then we have this, then we can, understand these sort of continuous symmetry transformations. By smoothly, we meant that there is some notion of closeness in the group. Okay, then we said that it was very useful to parameterize this whole thing, things such that when you had this alpha equal to 0, then that is something that corresponded to the identity element. And now suppose we expanded things around alpha equal to 0, then we had, so then we, if we looked at what the generators would be, then we could expand this at uh, some sort of region around the identity, and so that there these xa's essentially became the notion of the generators of the group. This was very useful, this was very important. And although you can speak about these generators in an abstract sense, what we are going to be doing, since we are interested in physicsy applications, is that we will be interested in trying to understand this from the point of view of particular representation. So now, I said that you can go away from the identity in various ways. One of the ways to do it is this, exponential map, where you take this, where you move at a fixed direction by raising the infinitesimal group element to a very large power. So if you take this infinitesimal group element and you raise it to a large power, it just means that you can exponentiate this. This is the exponential map. And this is this exponential parameterization, if you wish. This is a very useful, because these what we are interested in doing. Why is it useful to speak about the generators of a group rather than the group itself? These generators actually form a vector space. You can add them, add them together, multiply them by real numbers. And what you can do is you can refer to any one of these things, any one of the elements of this linear vector space. You can call these things as generators equivalently. Then what we said is, we defined the notion of Lie algebras. And we didn't define it. We sort of tried to figure this out. And what we said is, this was trying to understand this better. So if we looked at group elements that are generated by two different linear combinations of generators, in general, these exponentials will not commute amongst themselves. And then but on the other hand, it has to be that this forms, these are at least close to the identity. Since these exponentials form a representation of the group, the product also has to be the exponential of a of a particular particular generator, because the group, this is going to close. So what we do is we take these and we expand it and we find something interesting. What we find interesting is that once we do the do the expansion on both sides and so on and so forth, we find that there is going to be a notion of a Lie algebra. So we exponentiate and we match both sides, and we say that this has to be true for all alpha and beta. And once we do that, it's very clear that these generators must form an algebra. And this particular algebra, the very remarkable thing is that you can push this more and more to higher and higher orders. And just by the fact that this, the generators have to form a closed algebra, makes this group property hold. And this is sort of, I mean, this is a remarkable thing, and this is sort of the, I mean, this is going to be called the Lie algebra of this Lie group, and this is going to be central to our understanding. Okay, so that was that. Now let's go on to saying something about more things about representations of this group, and representations of the Lie algebra. Now we are going to discuss something important called the adjoint representation. Okay, now the representations that representations, not representations. What I wanted to say out here is that the let me correct myself, not representations furnish a representation, structure constants. So what is happening is, so you remember that this in the Lie algebra, these FABCs are things that are called, structure constants. You remember that because you can flip A and B, and then this gets a sign, so this side also has to get a sign. So these have to be antisymmetric in the first two indices. And we also said that if we were to have unitary representations of the algebra, then these FABCs have to be real. So these are things that actually characterize what your Lie algebra is. Now suppose let's look at this. So XA, XB. So what we want to do is we want to find out what the Jacobi identity this means. Okay, so that as you would remember is XA XB XC plus XB XC XA plus the third one is equal to 0. Now what is each individual term? So XA XB XC is XA, and let's use the Lie algebra here. This means that this is going to be some XD and FBCD. Now this again, you can apply the Lie algebra again, and what we find is this is FBCD FDE ADE XE. Okay. If you go about the same way doing it for each particular thing, then what you will find is that you will find that the Jacobi identity now becomes the product of two F's and the sum of these three terms. Okay, so that is what is going to be the Jacobi identity here. Now let's define our matrices in a certain way. Okay, let's define our matrices TA, which are going to be, so we define these things like this, that TA, so the BCth element of TA is FABC. Okay, IFABC if you wish. Then what happens is if you plug this into here, what you find is that this actually reduces to just TATB is equal to IFABCTC. So this is going to be homework for you guys. Just try to figure this out. Just do this explicitly. You will see this happening. So what is happening? What is happening is this is what my Lie algebra was, right? So if I take my matrices of, the matrices which denote the Lie algebra, so a representation of the Lie algebra, if I take it as this, then it's very clear that this is going to furnish a representation of the algebra because of the mere fact that Jacobi identities have to be satisfied. And if I just put in TABC is equal to IFABC, the thing, the Lie algebra essentially boils down to this, and that is always going to be true. So what we find is that the structure constants themselves furnish a representation of the algebra. This is going to be called the adjoint representation. Okay. The dimension of a representation is the dimension of the linear space that it acts on. So the dimension of the adjoint representation will be given by the number of independent generators of a group. Okay. Also, since we define things like this, if my FABCs are real, then we see that the generators of the adjoint representation are purely imaginary. That's another thing to keep in mind. All right. Now let's now turn to trying to see how to go from a linear space to a vector space. So what we need to do out there is also define something which is a scalar scalar product, right? So a good one here is the trace in the adjoint representation. So let's see what we want to do. So let's look at x's, and let's look at a transformation xa prime. This goes to some lab into xb. Okay. So what is happening? Some xa primed, xb primed. If we do this and we look at the algebra, then let's just go through this, and then what we'll find, you just need to turn the things around in your head, and this is what you'll get. So what you need to do is you need to find out how you are going to do this. So you write down this in terms of write down each of these guys, xa and xb, in terms of lab. Xa primed is LCDXC, and also do it for the other ones. In that case, what you're going to find is that this reduces to something like, so you are going to, so then so what you do is let me just write a few of the steps down. So this is what xa primed xb primed minus xb primed xa primed. This is going to be equal to LCD XD into L EF. This is not sorry, X. So let me make sure that I have my indices right. L AD XD and L BE XE minus, again, two of these guys, and then what minus stuff, and then you use the fact that XDXE, so commutator of XDXE is going to be IFDEFXF, and then just sort of do the algebra which is here. So again, I leave this for you as an exercise. So what you find is at the end of the day, you are going to get, this is going to be F primed ABCXC. And what you'll find that under this map, F ABC goes to F prime ABC, which is given by this expression. Okay, there are L's and there is an F as well. If we now define a new TA with the transformed F such that F, T ABC goes to T prime ABC, which is going to be something like this. As you see, this just comes from here itself. Then, if you are just thinking about the matrix and not about the BC's sort of indices out here, you're going to get something like this. Okay. So what is happening? So a linear transformation of the x's is going to induce a linear transformation of the ta's, which involves a similarity transformation and some linear transformations on the exit on the label A that sort of labels the particular generator. Now if we do this, if we look at the trace, so the trace is going to go to a trace of t prime ta prime tb prime, which according to this map is going to get you something like two L's out here and the trace. The rest of the things go away because the cyclicity of the trace gets rid of this L inverse L stuff, because you can cycle that around and that'll just go away. Now what we can do is that we can diagonalize this trace by looking at by choosing some appropriate L, and so we can call this T. This is going to be some delta AB. Okay. We can rescale. Rescale the generators, but we will not be able to change the sign of it. Okay. So this is going to define something which is a class of Lie algebras that are called compact Lie algebras, and so ta trace tatb is going to be some lambda times delta ab, and in this basis, the fun thing is that in this basis, if you just look at what this is, then you'll find that the f of abc is going to be going to make sure that the structure constants are absolutely antisymmetric. Okay. This again is something that I leave as an exercise for you guys, but just try to see if this is something that you can do. All right. So okay, this was supposed to be an exercise, so I'm not going to show that to you. So lastly, what I wanted to say in this very short lecture today is the idea of an invariant subalgebra. Very like the invariant subgroups, the notion of an invariant subalgebra is that if you have some set of generators which goes into itself under commutation with any element of the algebra, then that particular subalgebra is called an invariant subalgebra. More clearly, if you wish, is more so you can look at a generator X. If X is a generator of the invariant algebra, invariant subalgebra, and Y is the generator of the full algebra. So let me write subalgebra here, invariant subalgebra, and Y is the generator of the full algebra. Then what is going to happen is Y of Yx, commutator X, is going to be a generator of the invariant subalgebra again. Okay. So when exponentiated, this just means that this invariant subalgebra is going to give you an invariant subgroup. So you can take H as e to the ix, G as e to the iy, and so G inverse Hg is going to be ix primed. So where ix primed is going to be given by e to the iy minus iyx e to the iy. So this is going to be x, yx, yyx, and so on. Remember that this is a part of the invariant subalgebra. So if that is the case, then this is a part of the invariant subalgebra. As a result, this whole thing is a part of the invariant subalgebra, and the whole thing, order by, term by term, this is going to be true. So if X is going to be, if X prime is in the subalgebra, then e to the ix prime is also going to be in the subgroup. Okay. Very clearly, the whole algebra and zero are trivial invariant subalgebras, and an algebra which has no non-trivial invariant subalgebra, again similar to a group, is going to be called a simple algebras. Okay, and very clearly, if you have a simple algebra, this is going to generate a simple group. We are going to be speaking about the notion of simple algebras, and we are going to be speaking about the notion of semi-simple algebras as well as we go ahead. So in this very short lecture for the day, what we have learned is that we have this notion of we have this notion of the representation of the adjoint representation of the Lie algebra. That's something that's made up of the structure constants. So structure constants themselves furnish furnish this you know uh, representation of the Lie algebra. This is called the adjoint representation. And then we saw a few more things related to the adjoint representation. And at the end, I told you a little bit about invariant subalgebras, which are related to invariant subgroups. We shall take this discussion forward, and we shall try and distinguish between Lie algebras and Lie groups in the next lecture, which is going to be there with you shortly. Okay. All right then. So so far that's all for the moment. Thank you all. But I understand this was a short lecture, but it has some important things. I would like you to go through that and try and understand it well. Very good. So I stop sharing and I stop recording. See you next time, Rod.